So, I hope you're interested in PDPs and that kind of stuff, right? So, for those of you not familiar with what a PDP-8 is, there's the picture of the PDP. And we have additional peripheral there. You can see piled on top of an AM radio, and that is actually significant. If you come over to the booth, maybe we can demo the significance of the clock radio there with this theme that we have today. Anyway, a PDP-8L is a 12-bit computer, and it has an accumulator and 4 kilowords of 12-bit core memory, so a word is 12 bits, and you have 4 kilowords of actual core memory. Parity was optional. And the box contains a spot for a teletype control and a high-speed paper tape reader and punch controller. And then if you want any more devices, you had to get an expansion box, which is about the same size as this thing. I've never actually seen a real one myself, but you could get an expansion box that you could put disk controller and tape controller and all kinds of things like that in it, okay? And there are cables, a set of 8 ribbon cables that go from this box into the expansion box, okay? So me not having an expansion box would like to have a disk and tape drive and all those fancy things. So I thought, okay, well, what can I do to provide the functionality of the disk and tape in, without having the expansion box? So I thought, well, okay, it has those 8 connectors in the back. Let me see, scroll down here a bit. Okay, yeah, I have the little picture here for you. So this is the card cage inside that. This is sort of you can see the pins there, and those are the pins on the back side of these connectors here. So here is all the processor in here. Here's the actual 4K memory core stack here. And up in here was where the paper tape controller would plug in if you wanted a high-speed paper tape reader and punch. And in here, the teletype controller would plug in here, okay? And then in here, these were the spots where the cables would go to the expansion box. So you'd plug the cables in there. But you can see here, well, kind of see it, hopefully you can see it. This is where my little fancy boards plug in, okay? So I designed some boards that just plug in the slots where the cables went, and it will provide the functionality of disk drive and tape drive and all that stuff, using modern SD card, right? So you put your file on there that's an image of a disk drive or image of the tape contents. You put it on the SD card in here, and then this board will serve that up to the processor as a normal disk and tape. And it boots, the disk operating system that came with the original PDP-8s and all that great stuff. Okay? Okay, so that's what the situation is here. So the basic goals of the project was to make boards that plug into the original slots and to provide all the I/O functionality that went in that expansion box. Okay. And fortunately, it turns out that this can also provide the teletype and paper tape reader I/O if you just leave these cards out of the processor. So you just yank out the paper tape controller and the teletype controller, and it will go to the regular I/O bus and get them out of this FPGA card, okay? So the FPGA can basically perform all the I/O for the processor in this case here, okay? So back when I was thinking about making this, okay, so I sort of had 2 design considerations. Can I use a Raspberry Pi? Or do I have to use the Z-turn card? And I'll talk about what the Z-turn is. So a Raspberry Pi, hopefully you're familiar. Oh yeah, this is what the thing looks like when you pull it out of there. There's the FPGA card, and then here are all the little connectors that plug into those I/O slots down here. And there's a picture of the FPGA card again. Anyway. So here is a comparison of what you get on a Raspberry Pi versus what you get on the Z-turn Zynq card, okay? So Raspberry Pi has an ARM processor on it you might be familiar with, and it provides GPIO out, and you get 28 whole pins of I/O pins on it, okay? And the GPIO circuit is basically a simple parallel port, okay? So your ARM processor can read and write, bits on this 28-pin connector, okay? There's also like a BeagleBone board, and that gives you 60 pins, okay? So that's the kind of thing you're looking at, but again, it's just a simple parallel I/O port. So any programming on those bits has to be done in C code in the ARM processor, all right? Now a Z-Turn card has the ARM processor just like the Raspberry Pi, and it can run the Raspberry Pi OS actually, but it has its own version of the kernel, the Zynq kernel, okay? But it has this wonderful glob called the FPGA. They call it a fabric, but FPGA fabric. And it has 85,000 flip-flops thereabouts, right? So you think of a big bucket full of 74 chips. That's what you're looking at. You have to put together, right? So, and it gives you 90 pins on the connectors, okay? So that's a lot of fun stuff. Now, the thing that makes the Raspberry Pi and probably the Beagle board not all that usable is that it can do a few million operations on this connector at a time. Your C program can read and write maybe, 2 million, maybe as many as 10 million IOs per second on that. And PDP-8 is putting out pulses, 200 nanosecond pulses you have to be able to respond to. And that would be tough to be able to read a pulse in from those 28 pins when you can only go, a couple million times a second. You're going to start missing pulses and stuff like that. Whereas with the FPGA card, you're talking about a 10 nanosecond cycle time, so a 200 nanosecond pulse, you're going to have 20 clock cycles out of the FPGA, so it can easily capture all those pulses and respond to them, okay? So that's what makes the FPGA a reasonable, option for making this project work. Okay, you couldn't really do it with the Raspberry Pi. Now there's you might have heard of the Unibone board, which is for the PDP-11 Unibus, and it uses a Beagle board. But you'll notice on there they've got a lot of TTL chips in there to do the operations that require the fast response times. And I don't have any room to put a bunch of TTL chips on here. Okay, these little chips here, the only chips I have in here are 3 volt to 5 volt converter chips here. So I don't really have room to do a bunch of discrete circuitry in here. So really the FPGA was the easiest option for me. All right, so the next thing to wonder is, okay, so you've got 85,000 flip-flops in here. How are you going to program those, okay? So fortunately, they make it easy. At least I think it's easy. And the thing about this is programmable. So each PDP device, like a disk drive, is just a bunch of software in the FPGA. So you just program the FPGA like you program any other program, and then it can process the IOs coming out of the PDP. All right. So the language that's used to program these, well, there's actually 2 languages. There's Verilog and VHDL. I don't use VHDL that much. I use it at work, but for this project, I like Verilog. I think it's simpler and easier to use than VHDL. Now, there are 2 basic types, or 2 classes of Verilog code, okay? There's synthesizable, and that means something that can actually create gates and program into an FPGA. So synthesizable VHDL, the compiler can take that and then program that into an FPGA, okay? There's also a superset called simulation VHDL, and that actually has print statements in it. Now, you can't program a print statement into an FPGA, but that's used in simulators, and you can put the print statements, or actually it's called display, but you can put the display statements in your code for debugging and stuff like that. I have never really bothered much with that, so I don't know too many details about that. just the general concepts. But I just focus on the synthesizable VHDL. And the reason why I'm talking about this is, you can go on the web and there's, billions and billions of pages on how to do Verilog. So, and you'll find, display statements, and I think it's weight or something like that, where you can give it pauses of so many nanoseconds. That's all simulation stuff. And you can't program that into an FPGA, so it's just a word of caution if you want to, study this further. Okay? So I'll just give you, the basics of how to do Verilog. So when you walk out of here, yep, you can start programming Verilog. Okay, so it's quite simple. Okay, if you can draw schematics of gates and flip-flops, you should be able to do Verilog, right after that. So you have a gate here. Here's a little NOR gate. So if you want to do the Verilog equivalent of that, there it is. Assign, blah, 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 right? So you have the NOR out. That's why I said NOR out. You have to give the signals names, so you have to name the gates, your outputs of your gates. And so there's a little NOR, right? A NOT and an OR. So there's your NOR gate. So you can take your schematic and you can write out a little Verilog statement, and voila, there you go, right? So there, you're programming Verilog, okay? Flip-flops, of course, you might think is a little more complicated. So here we have an example here. I put 3 flip-flops, okay? D flip-flops, the simplest type of flip-flop we use, okay? And you can say, okay, always at positive edge of the clock, okay? So that's telling Verilog, okay, we want these flip-flops to trigger on the positive edge of this clock, okay? And output 1 here comes from data 1. So when the clock clocks, data 1 is going to get plunked into this flip-flop here, okay? Into this output. And output 1 is going to get kerchunked into output 2. And then here you can actually put a gate and mix a gate in here. So you can make these as complicated as you want, okay, this Boolean statement here. It doesn't have to be just a NAND gate or just a OR gate. It can be a very complex Boolean equation, okay? And so we take the output of this NAND gate and we clock it into this flip-flop. Now, the thing that makes Verilog different than, say, C programming, you can see, yeah, this kind of looks like C, okay, is that all of these are done in parallel. So you can see here, okay, data 1 goes into out 1, but then it's the old out 1 that goes into out 2. It's not this new out 1, okay? This thing says pause edge of clock, so this kerchunks every 10 nanoseconds, because that's what we have our clock at, or whatever you have the clock. You can put whatever clock frequency you want. With this chip, it's 100 megahertz. So, every 10 nanoseconds, it takes data 1, puts it in out 1, takes the old out 1 and puts it in the out 2, and then takes whatever coming out of this NAND gate and puts it into out 3. Okay, so that's how these 3 flip-flops work. Okay, and the one thing you can check is make sure you didn't make any assumptions about what order these are done. They should be able to put them in any order, and it should still mean the same thing. If you say, oh, I put these in a different order, it means something different, then something's wrong and you have to rethink what you did. So these statements could be flipped around in any order. So you could put this, out 2, out 1, out 3 in any order, and it still should mean the same thing, okay? The compiler is going to treat it the same. So hopefully in your mind you're thinking, all right, this does the same thing. And you notice this makes a shift register, okay? So this is how you make a simple shift register, right? Okay. So those are the big things you have to get about doing Verilog. Once you get those concepts, it's pretty much smooth sailing from there. You can, again, do a flip-flop. There's your flip-flop, okay? There's a gate. And what more do you need besides flip-flops and gates, right? Because that's what all your circuits are made out of, okay? Now, Verilog makes some things that make this a little simpler to do, okay? So you're not stuck with just these simple assignments like their if statements and case statements. Like, okay, a case statement, like switch and case in C, well, that's a multiplexer, okay? So you can make a multiplexer with switch statements and that sort of thing, okay? Like over here, I have a little example of I have 4 flip-flops here, and flip-flop 1 always gets from some combinational logic, and here's flip-flop 2 likewise. And then this flip-flop here, this would be some Boolean thing, if A and B and not C or D, blah, 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 whatever you wanted to put in there. Kerchunk these flip-flops. Otherwise, it would just leave the flip-flops with whatever output they had and just not clock them that time through the loop, okay? So Verilog gives you if statements. And there's also switch case, which I show an example of a little later on. All right, but you can just stick with these basics, here. If you can draw a schematic, you can translate it to this and this. And, you could, go to town with just that stuff. Okay. You can also use, if you want to use if statements with your gates, there's this funny little thing, always at star begin. And that just says continuously run this loop. So these assignment statements are just continuously run, which means it's basically some gates. Okay. So it's just always going to compute this continuously, okay, which is the same as this. In this case. The only difference being the reason why you would want to do this is if you had like if statements or case statements. You could use those. You can't put a case statement inside an assign, but you can do a ifs and cases inside always loops. All right? So that's programming Verilog, basically. And there's another little discussion there about using always for gates. Now, the thing about using always for gates is it's a little tricky. You want to make sure that when you assign a gate that you always, end up not assigning the gate. If you have some if path through there that doesn't do a gate, Verilog will try to conjure up a latch for you, right? Because if you say if blah, blah, assign gate output such and such, unless you put an else clause on there, it's going to say, oh, he wants the gate to hold the same value that it did last time, in which case it has to do a latch for you. And FPGAs aren't that good at doing latches. They're optimized for doing flip-flops. And the compiler usually complains at you if you give a latch. Say, you really want a latch? Okay. And the thing about using latches is if you want to do a latch, you can always do a latch type functionality using flip-flop, okay? So here we have at pos edge of some clock, so that means it's a clocked flip-flop. And we say, okay, if the latch gate is open, kerchunk the latch input over into the latch output, all right? So you can do latch type functionality using flip-flops. And the reason why we don't like using latches in FPGA is there's a big clock bus, okay? And a clock bus goes around to a bunch of flip-flops. And the whole FPGA fabric is based on flip-flops. So it has flip-flops and a little multiplexer and, programmable matrix and their, proprietary magic that makes the whole thing work on each flip-flop. And if you did a latch, well, then it's not going to be able to use the flip-flop anymore. And plus, there's timing analysis it does on the flip-flops to make sure, okay, how much goop can I put in here? Like here, I just have a straight wire. But here, in reality, these AND gate inputs are going to be connected to other flip-flop outputs, and maybe this flip-flop output circulates around in here through a bunch of combinational logic, okay? And it's going to take so much time for the stuff to get through all these gates and stuff before it comes around back in here. And how long can I take? Well, if I run this thing at 100 megahertz, that stuff has to flow through all these gates that I give it in 10 nanoseconds and be ready to go when that clock comes along, right? Okay. So the compiler will tell you, do all your circuits meet that criteria? Will their data be ready in 10 nanoseconds, okay? And if you start doing latches and stuff like that, it confuses that analysis and it can't do it. So that's why you always try to make your stuff out of flip-flops and don't use latches. Another thing is that the design should be synchronous because, like I said, there are these clock buses in the flip-flop fabric where it is very optimized for putting the same clock on all the flip-flops. Okay, like you'll notice in the old processor designs, they just have arbitrary things going to flip-flops and pre-clears and presets just willy-nilly all over the place, okay? Whereas with the synchronous design that you should use in a FPGA, everything is clocked on this clock, okay? So you always use these always statements with the same clock as much as possible. The only time you would not do that is if you're doing something really fancy, like maybe you're making a gigabit Ethernet switch or something like that, and then, you know, that's a little bit beyond my knowledge. But, you know, for things like this where we're working with, you know, inputs that are on the 100 nanosecond range and our FPGA is clocking at 100 megahertz, you know, in the 10 nanosecond range, we can easily just put all our flip-flops, tell them to clock, you know, kerchunk, kerchunk, kerchunk at, you know, 10 nanoseconds a cycle. And, you know, you're going to be able to program everything. Plus, it's very easy to reason about, okay? It's almost, you know, as simple as, you know, working on C code. Okay, you're going to have all your inputs set and kerchunk, ready to go. And then, you know, they filter through and compute the next state, kerchunk, ready to go. And everything always happens kerchunk, kerchunk, kerchunk. So it's very easy to make a very reliable circuit that way. You don't have, oh, the timing case of, okay, the setup time on this flip-flop, you know, and, you know, the whole time, and then I've got another flip-flop triggering asynchronous compared to that. No, all the flip-flops are all kerchunking at the same time. So that's why you try to do that. And the compiler will start to scream, oh, I can't analyze the circuit if you start doing funny things with clocks. You can tell the compiler, okay, the relationship between these two clocks is so many nanoseconds apart, and it starts getting very complicated very quickly, as from my standpoint anyway. I just take the defaults and just use the same clock for everything, and that's worked fine for this circuit. All right, and down here, I don't know how well this shows. Oh yeah, I did a magnified one. So here it's telling me, this is the setup time. So I have, obviously since I'm clocking at 10 nanoseconds, I have some circuit path that goes 9.6 nanoseconds, okay? So I'm right up to the edges. This is the worst case setup time, and I have slack. It's worst case slack. I don't remember what the N stands for, but this is the worst slack. What's that? Negative. Okay, negative. Okay, and so this says, okay, well, you've got another 400 and some odd picoseconds more for this path. Yeah, and these gates in these things, you know, are these, you know, so many nanometers wide, so they only take a few picoseconds to get through these gates. So anyway, the compiler is telling me, well, you've got a slack of, you could take up another 400 picoseconds along your longest path, okay? And then over here is the worst hold slack, 57 picoseconds. And this is the hold time, right? Because every flip-flop, when you clock a flip-flop, you have to have the signal in place so many, you know, picoseconds ahead of the clock, and you have to hold it in place for so many picoseconds after the clock. And this says, okay, well, you're holding it for an extra 57 picoseconds, which is good, right? You don't want to hold it for too few picoseconds. And the slack time says, oh, I've got to set up an extra 400 and so many nanoseconds before it has to be in place, okay? Now, if you did do something that was complicated Boolean expression, you know, blah, 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 maybe you try to add a bunch of numbers and stuff like that, and it doesn't meet the 10 nanoseconds, okay, you sort of had two choices, okay? So first of all, you have to recognize, okay, the compiler will scream at you and say, okay, well, you've blown past the setup time on this particular circuit. So it will scream at you and tell you, okay, you've got to fix this. So you have to recognize and say, okay, well, it's going to take me 20 nanoseconds. And you can either put something, you tell the compiler, okay, this circuit path I know takes 20 nanoseconds. I'm not going to expect to get the output in 20 nanoseconds. So I'm handling that myself. So don't complain at me about it anymore. Or another thing is, you can just break it up into two 10 nanosecond computations and kerchunk, you know, so you just stick a flip-flop in the middle of the computation and have it go kerchunk, and that does the first stage, and then kerchunk for the second stage, and the compiler's happy, and you're happy too, hopefully, okay? So you know that the signal is going to be ready in time anyway. The compiler will tell you. That's the main point of all this exercise, okay? I didn't need to do anything fancy in this circuit that I did. So anyway, the compiler will tell you, so you don't have to worry about, oh, is this going to make it, you know, and do it by testing. No, the compiler will tell you, and I've never had a problem with the compiler being wrong about that, so I think they've got that down pretty good. All right. We talked about latches, all that great stuff. Okay, so a few more things about Verilog. How do you declare? You have to declare your outputs. This is one thing VHDL has over Verilog. Verilog, you have to tell reg or wire, okay? So reg, you can think as a register, which you think is a flip-flop, but it's not necessarily a flip-flop, unfortunately. Wire is wire, so that's always gates. I don't know of any time where wire is not a gate. There might be an example, I don't know. But anyway, wire is used when you use it in an assignment statement, and you can also combine the assignment statement with the wire statement like that. So that's got an a wire and an assign. Reg is always used if the thing is written with an always loop, okay? So reg could be a gate when you use an always loop for making gates, okay? Otherwise, if you use the clocked always loop, then it is going to use flip-flops for it. With VHDL, you just call it signal, and the compiler figures it out. But unfortunately, with Verilog, we have to use reg and wire. And the compiler will complain if you use the wrong one. So why they did that makes no sense. Obviously, the compiler can figure out what it should be. So, but you just have to live with it. That's about the only downside of Verilog. That's the only thing about Verilog I don't like. So that's not bad. All right? And then...
System Verilog, and then they call it logic.
Oh, okay, yeah. I don't know System Verilog. I never learned it. But yeah, they might have cleaned some of that stuff up in newer versions. Yeah, that's good. Okay. So now, let's say we want to make a board out of this stuff, okay? So you, in Verilog, a board is called a module, as you might suspect, okay? And from a hardware perspective, okay, you're modeling a circuit board, okay? And you can plug a circuit board into other circuit boards, you might imagine, in the real world. So in Verilog, you can plug modules into other modules if you want, or you can have the pins go to the outside world if you want, okay? From a software perspective, they sort of behave like macros or inline subroutines, and you can instantiate them in other modules. So you can build up a hierarchy of modules if you like, okay? It's just sort of a perspective, okay? Hardware perspective, you can think of, you know, circuit boards plugging into other circuit boards and things like that, right? And copies of circuit boards. So each time you reference a new copy of a module, that's, you know, a new blob of transistors. So it's more like a macro than a subroutine call, okay? So think of it as a macro from the software perspective, okay? So here, I've made a little 8-bit processor for you, okay? Or I've got it started. So module processor, so I want to call this a processor. And here's my, you know, 100 megahertz clock coming in and a reset button here. And I have output register, the memory address register, memory data is a bidirectional bus. Okay, so you can give a bidirectional bus that way. And here's a little signal going out to the memory card. Oh, I want to read memory. Oh, I want to write memory. And here the memory is telling me, oh, I'm busy doing that. I haven't finished it yet. And I detailed those out here. Okay. And then I have a big always loop here. So this thing just clocks along at 100 megahertz or whatever. If reset, you know, I'm going to clear all my, initialize all my state. And then here, the case statement. So this shows an example of using a case statement. So depending on what state I'm in, I'm going to do these various blocks of logic here. So to start out with, okay, I'm going to do the typical thing a processor does, right? It puts the program counter on the memory address bus, tells the memory I want to read, increments the program counter, and then changes the state to state 1, okay? So notice here I increment the program counter. If this statement was written up here before this would still be using the old, pre-incremented program counter. So I could put these in any order I want, okay? But this, I write it like, it makes the most sense to me, okay? So I want to put the program counter out, then I want to increment it, okay? But here's, state 0 does that blob, and then down here, it's going to say if the memory is not busy, then I'm going to, grab the data from the memory and put it in the instruction register, tell the memory I don't want to read anymore, and then go on to state 2. And down here, you can start filling in, all the instruction decoding stuff in here, So you can make an 8080 out of this if you wanted to, or you could make this a 32-bit program counter and 32-bit address and make a VAX out of it if you want it, right? So there you go. You're not going to make a 6502 out of it because we do not make chips with 8-bit stack pointers. Anyway. My editorializing, all right. Okay. Okay, so now you may ask yourself, okay, I've done all this crazy programming here. How the blink do I make this stuff work? How do I debug this stuff? Because bugging is easy, debugging is a little harder. So they make this little box down here because you can't stick a flip-flop probe on here, and see when the state changes, right? You can't stick a flip-flop and scope probe in the middle of this chip. Okay, so they make this little magic box here called an internal logic analyzer. Okay, and it's this little square box here, and a ribbon cable that goes up to the FPGA card, and then here's a USB cable that goes to the PC where you're running the IDE to compile this stuff, right? And let me give you a little sample output here. So like here I set this probe up, I programmed this probe, and here's the memory start pulses coming out of the PDP saying start a memory cycle. And the PDP also generates this time state 1 and time state 3 pulses. That's kind of hard to explain, so I probably shouldn't have bothered with those. But here is the FPGA responding with, okay, memory start. PDP said start reading memory, and here's the FPGA saying, okay, I've read memory. And so the data is valid on the data bus. And then this one down here, is that, yeah, that's the that's the mem done pulse, which says I'm done writing. These things have core memory, so every memory cycle is a read followed by a write, because as you might know with core memory, when you read core memory, it wipes the core memory location out. I think in the PDP-8L's case, it sets it all to zeros. And then for any writes, you have to write the 1 bits back in there. I think that's the way it works. It's either that or it writes all ones. It can't do one or the other. But I think the PDP-8L writes zeros. So there it is. It's always a read followed by a write. Even if you're just reading, you have to write that exact same data back on the write cycle. So there's the FPGA responding with read done, write done. I can't remember what those others were for. But anyway, it's just an example of things, you can use this probe to see what's going on in the chip. Okay, so you're not left just scratching your head, Another way to do it is, of course, you can route these signals out to pins on the bus, or out to pins on the card, and you could hook an oscilloscope up and read, particular pins if you want. Okay, but this is another way, to debug stuff down inside the FPGA, so you can debug things that way. All right? Okay, so now, how do we use this for the PDP-8? We know how to program Verilog now. So what does the PDP-8 have? How can we program that? So here are a bunch of buses. So the PDP-8, was designed to work just with that box, right? Their expansion box. It wasn't designed to be, a general, I/O sort of bus. So it's not very neat, but it's neat enough that, it's definitely workable, okay? So there are 7 12-bit data buses coming out of that PDP, okay? And they're all 12 bits wide, so that'd be 84 pins, and that's going to use up almost all the 90 pins out of the FPGA, which is no good. You want the control lines, I wanted the control lines to be not multiplexed at all, so I have direct access to all the strobe signals and things like that, okay? So I multiplex the data buses, plus it gives me the most bang for the buck, So here's the 7 data buses going into the PDP, and then I multiplex them into these 3 buses on the FPGA side. Okay, and these are actually neatly organized into the little groups of connectors on those on the circuit boards, so that made it easy to do, easy to wire up. All right. So, control signals you have, I showed like the mem cycle start, and there's I/O pulses coming out of the thing, and there's a signal for, whether the thing is running or halted, and a bus initialize, and address extension bits, DMA granted, interrupt acknowledged, those sorts of things that you might expect. And then coming out of the Zynq, going out to the PDP, whether or not you want to use the core memory or you're going to use the external memory, memory read complete, write complete, interrupt request, those sorts of things, okay? So those control signals are not multiplexed, okay? We want the FPGA to be able to grab them as soon as they happen. We want the FPGA to see them as soon as they happen. Whereas these data bus signals, okay, we can take our time, switching those back and forth. And by take our time, it takes like 30 nanoseconds to switch one of these buses around. So that's plenty of time to be able to grab, things that are coming in the 100 nanosecond range, 100, 200 nanoseconds. Yeah?
Is there external logic that takes the pins off of the bus and it's used as a multiplexer, so it's signaled by the
Yeah. Like I showed earlier on, there's those level converters, the 3 to 5 volt level converters. They also can do multiplex because they can be tri-stated, so they can do the multiplexing in those, yeah. So Coda was two for 1 on those, okay? So that's how I decided how to multiplex things, as I figured I'll get the most bang for the buck by multiplexing the data, because I want to keep access to the control lines direct. And so there really was nothing wrong with the hardware. When I put the hardware together, designed the hardware, and had the circuit boards made, okay, they pretty much worked, okay? I did a Rev 2 board because the drivers specified that I think at 25 milliamp, that they could do 25 milliamps, and the worst pull-up on the PDP was, like 18 milliamps, and yeah, that's kind of pushing those little driver chips, so I made a Rev 2 board that had a bunch of transistors to drive those bus lines. But other than that, it wasn't like, oh, geez, I really should have put an AND gate here, or that sort of thing, because it's all done in the FPGA. Yeah, there's a lot of software work on that FPGA. I spent a lot of time getting that right. But the hardware pretty much just worked. So you can sort of relax when you do one of these things, okay? Because any goof-ups, you can sort of make up for. All right, so we're going to kind of blitz through the rest of this here. So this is basic layout of the FPGA stuff, okay? So here's the PDP-8 and most of the FPGA logic. And it just presents a bunch of registers, a bunch of, these are ARM processors, a 32-bit, RENs, Raspberry Pi OS with a Raspberry Pi Linux. There's a 4K memory page, right? The GPIO thing is just, it has a 4K page, but it's just a parallel I/O port. These here, you make up whatever registers you want. and you can plunk them in a 4K page, or if you need 8K or whatever, you can make it as big as you want. And you tell that, Vivado compiler how big a page you want and wire it up. And also, this FPGA provides extended memory to the PDP-8, so it gets the full 32K that the PDP-8 architecture supports. And it's a dual-ported RAM inside the FPGA. The FPGA has like 4 megabits of RAM you can configure however you want. So I take 32K by 12 and make a little RAM in that the PDP can access through this logic here. And then that maps into a 128 kilobyte address space that the ARM processor can access. So, and then here are all the registers for the devices, that sort of thing. And one design decision I made about these registers is I didn't want any side effects. If the ARM goes and reads these registers, there's no side effects on the state of the FPGA. So if like the PDP-8 is saying, print a character on the teletype, okay, that's going to go get plunked in one of these TTY registers. The ARM reading that register is not going to tell the PDP, oh, okay, well, I printed the character. The ARM has to actually go and write to this register to tell the PDP, okay, I've printed that character. And the reason why I did that is so I can write a program that continually dumps these registers out. Yes?
Just a question about the extended memory.
Yeah.
Does the PDP-8 think that that's core memory? Does it write back?
Yeah. Yeah, it looks like core memory. That would be very difficult. That would take a lot of wire wrapping on that backplane to hack that. Yeah. So, yeah. Anyway, okay. So the thing that allows me to do, not having this state alterable, is I can write dump programs, is dump these registers out continuously, which helps a lot with the debugging. Anyway, yeah, so he's asking about this core memory, or this memory here. Yeah, everything looks like the expansion box, at this point here. So the PDP is hopefully happy with that. I also have a little board here that I stuck on the front panel to read and write the front panel bits. Okay, that doesn't go back to the pins in back. So I made a little board that plugs into the pins on the front of the thing that give me access to the switches and lights. Okay. And Digital did something, I thought, well, geez, am I going to be able to override the switches? And Digital designed that front panel so that you can, oddly enough. I don't know if they did that, for automated testing or for what purpose, but it was a good thing they did, and I was glad they did, so I didn't have to hack any wires or anything like that. So I can override the front panel switches, which is nice. Okay. Yeah, we're pretty much out of time here. There's some little more details here. Anyway, if you want to look, there's this GitHub page here that you can look, at all the source code, and there's more pictures and stuff like that. Of course, I've got the exhibit booth over there in room C, so you can have a look at the result there. And I have a little music program, and we have some period correct music, so you can think of what kind of pieces we may have that are period correct for late 60s, early 70s. And you'll have to come by the booth to see which ones we've got going there. And yeah, so that's pretty much it. Are there any more questions in the few minutes we have left here? Any more questions for anyone? Yeah?
Your 32K there, is it? Oh.
Got that going.
Check, check. Oh, there we go. Your 32K in the FPGA, is it shadowing the first 4K or?
Okay, there's actually an option bit. So that 32K, if your core memory stack is not working, okay, this 32K will take over the functions of the full 4K, the original 4K. Or you can tell it to use the 4K stack if you want, okay. So yeah, good question. Yeah. So it'll work either way. Any other questions? No? All right. Well, that's pretty much it then. There you have it. And so hopefully, you could use this for other processors too.
I'm crazy all for